Quantum theory, the world of the smallest particles, is actually influencing mathematics. And I would even say that the future is for quantum mathematicians. Mathematics is also what mathematicians do. And we do this with our brain. And so how is our brain created? Well, many million years of evolution. And so I think our concepts are very much influenced by the things that we see around us. So we talk about space because we kind of move in space. We move in time. We count because we see objects. We throw stones, so we want to describe the path of a stone and its velocity. And so calculus, for instance, is based on the idea of speed or a slope. So I think actually our mind is very much kind of set by everyday experience. So you might think that mathematics kind of stops being effective if we move into a new territory, for instance, the very large, the universe, or the very small, the world of elementary particles. But the remarkable thing, this hasn't happened. So mathematics has been extremely successful in conquering, certainly I think, the physical experience. General relativity, or Einstein's theory, is a good example. He needed a concept of curved space. And it turns out that Riemann and others in the 19th century had already thought about it. They thought, well, you have 2 dimensions, 3 dimensions, why not have an arbitrary number of dimensions? Abstract thinking of mathematicians was kind of ahead. In quantum theory, even if you sit and meditate for 1,000,000 years, you wouldn't come up with the laws of quantum mechanics because it's so bizarre. So in that sense, nature had to force that upon us. And it was like a very painful process. We had to let go of many very cherished concepts. For instance, the fact that the world is a predictable system. Quantum mechanics is just the way nature works. You see it very clearly at the level of atoms and elementary particles. And if you take many atoms together, then in some sense many of the features of quantum mechanics are kind of washed away. We don't observe it because we are made out of like 10 to the 24 molecules typically. There are several things that you have to give up in quantum mechanics. The first is that you cannot know the answer to all questions. So for instance, typically I would say, well, there's this pen, I know where it is, and if I drop it, I know what the velocity is that it's moving. Quantum mechanics says that's all fine, you can know either the position or the velocity. So roughly half the questions are unanswerable. That's really bizarre, because how would I then describe a pen? But there's a second thing, which is that even if you want to describe how things move, they never have a specific answer. So like if you're a classical object, like a pen, now you would say, well, how do I go from A to B? Well, there will be a shortest path. If I throw a stone, it will go like this, from A to B. And I know exactly how it went, and this is like the optimal path, and I can calculate this, and mathematics is about this. Now, if you're a quantum mechanical particle, you are basically free to go on any possible path. So, and you could even have really very bizarre paths that goes all the way like that. And the thing that physics will do, it will give a certain probability for all these possible scenarios. If I, for instance, want to go from my work to home, I know pretty good what the path is I'm taking. But if I'm an electron that's moving, say, from one atom to another atom, it's more like these curves. So everything is in terms of chance. The quantum probability is something, it's a complex number, and if you take the absolute value squared, it becomes actual probabilities. So for instance, one thing that, because of these kind of funny things, what can happen is that instead, even if you think about where a particle is, now it could be either here or it could be here. And you might say, well, there's a certain probability it's in A and a probability it's in B. But a quantum mechanical particle can be for half be here and half be there at the same time. So this is very strange. It's like you take a point and you divide it in 2 fractions of a point, put one here and put one there. And so the rules of quantum mechanics are partly captured probability, but they have some kind of very strange phenomena built in them. And you have to kind of dig deep, and basically things happening all at the same time makes quantum mechanics very difficult to absorb. It's been said, if you say you understand quantum mechanics, that you're just lying, because this is something that in our intuition we simply cannot understand. Physicists were thinking about, well, we need some object, for instance, to describe the transitions in an atom, how we go from one state to another state. So, well, we need something, and then they discovered it's called a matrix. It is actually known, of course, in the mathematical literature. But to understand the concept that came in, like Hilbert spaces and wave functions, that was mathematics that partly was being developed at that time. But I would say then the physicists really ran off with it. And at this point, I would say mathematicians are trying to catch up and understand, not only the language, but also the power of the concept. Because there's something incredibly natural in quantum theory, which is perfect for the mathematical mind. Because mathematicians, they're not studying one object. They actually really always think about the whole family, the category, all possible objects. So all numbers at the same time, or all possible geometrical shapes. And what quantum mechanics says is that's like perfect, because I'm not considering one path, I'm considering the space of all paths. And in fact, I'm giving you something else. I'm giving you a way, indeed a probability of each possible path. So in some way, you can sum all over these different paths. We call this the sum over histories, which is, again, a very funny concept, because we think of history as something, well, certain things, certain facts that happened. For the quantum mechanical mathematician, history is all possible scenarios at the same time. And so there's a certain way to consider many different things at the same time. And so one wonderful application of all of this was in knot theory. So if you have a knot like this, connected like this. So I'm just drawing here the projection, but it's a certain trajectory in 3 dimensions. And mathematicians want to distinguish. This one is knotted, this one is not. And so if you're a knot theorist, you want to study knots in generality, the space of all possible knots. Actually, quantum theory comes to the rescue. It's a very efficient way to describe these knots. And young physicists are not that surprised anymore, as, for instance, Niels Bohr or Albert Einstein was, who was really fighting the concept. I often think, at some point there will be a generation of mathematicians that kind of grow up with quantum theory, and they will probably apply these kind of rules in a very natural way.
They are starting to steal your stuff, are they?
Exactly. So the remarkable thing is that there are some very deep mathematical problems, abstract mathematical problems, like this classification of all knots, or thinking of 4 or 6 dimensional spaces. Really purely interested from mathematical arguments. And now there's a bunch of these problems that actually have been solved using quantum theory. I think of it like a good mathematician has a toolbox that's filled with everything. Geometry, calculus, number theory, and the rules of modern physics should be there. It's just a very efficient way to deal with certain problems. And I think many mathematicians were surprised that the information was flowing in the other direction. Physicists are surprised because they see the quantum mathematicians, so to say, take these ideas and generalize them even further. It's like you have a very brilliant student and you're teaching the student everything you know, and then the student takes that much further. Because again, and that's the beauty of math, it is in some sense rooted in reality, but then it's not. It's hard to meet a mathematician that's not, doesn't think Platonic. It thinks that the prime numbers are just out there and they have nothing to do with the fact that there are 3 pens here. The number 3 is there. And so there's this kind of interesting kind of oscillation between math absorbing facts from reality, but then kind of take a flight of the imagination and go in directions that the physicists say, wait a moment, that was not actually our intent to go to do these kind of crazy stuff.
Has this emergence of mathematics coming out of physics been a difficult birth? Has it been something that has caused problems?
In two directions, I think. The physicists would say, well, math is very attractive, but it's like a black hole in which you can disappear, because you will be divorced from reality. With this, you have to tie yourself to the mast of the ship, not to be seduced by the beauty of mathematics, because many of the great insights in physics looked very painful and unelegant and ugly to begin with. It took some time to appreciate quantum theory as something beautiful. So that's the rivalry from the physics part. From the math part, I think it is that physicists are sometimes seen as kind of plumbers. They make their hands dirty. They deal with this messy thing called reality. It's beautiful as a mathematician. You can go in this Platonic world where there's a certain perfectness. So there was also, I think, quite a few mathematicians that weren't originally impressed with the physical ideas. They might say, well, you might kind of be, there's one or two areas where this is relevant, but not to my field, which is pristine. And then certainly, out of left field, there were some physical ideas that proved to be very, very, very powerful. And I feel it's like a wave. You think it won't hurt you till the wave hits you, and then certainly you are underwater. In physics, we have really a crisis. And the crisis is that we have two wonderful theories that describe the world. One is quantum theory. It's perfect for elementary particles. The other one is relativity, and it's used to describe large structures in the universe. But the point is these two things clash. And they clash because these physical laws of the large, they include events like black holes, and perhaps more important, the Big Bang, where the rules of physics break down. So this is quite remarkable that the theory that you have to describe reality has its own failure built into it. And we think that, in some sense, the only solution is to bring quantum mechanics in it too. So we somehow have to marry these two pictures. It's not enough to do quantum mechanics. It's not enough to do geometry. And we know this is happening because the universe is working. It's right now, while we're speaking, the laws of nature are perfectly working, and there's no breakdown anywhere. So that means that we have to come up with something deeper than geometry. Now, what is that? That's I think the big mystery, and we have some ideas. So the idea could be that geometry is something like thermodynamics, which is the theory that describes basically materials. So if I think of this table, it feels pretty solid to me, but I know it's a large collection of molecules. I feel the air around me and I feel a certain temperature. But there's no such thing as temperature. These are just molecules bouncing up and down. So could it be that just as this physical sheet of paper, if I zoom in, zoom in, zoom in, I will certainly see molecules and atoms and elementary particles, and there's no paper anymore. Could it be that if I zoom into space itself, at some point I see the pixels, I see something else? We were thinking perhaps it's pure information, it's like zeros and ones. So I find that absolutely breathtaking, because if we are able to come up with a piece of mathematics that is more fundamental than space, than geometry, I think it would be revolutionizing all of math.
Just imagine, trying to imagine these two huge objects, what they're doing to the matter, to the space-time around it. And the space-time must be going, oh my God, what's happening here? And it's flipping up and down, and they're just generating. These waves are beginning to propagate out. 350 kilometers is about the distance, to London. Then you've got 230 solar mass black holes sort of orbiting one another in this region. And so they're going at close to the speed of